These buildings are among the biggest man-made objects. They have been moved many kilometers across the sea and sunk down to incredible depths. They are made of reinforced concrete, built in massive mobile and floodable construction sites, then tugged to their final resting place. Troll A is the world's tallest building, and the Gullfaks C is the heaviest object ever moved. They were the first in a long line of massive oil platforms built over the last 2 decades that use gravity and suction to remain upright in the stormiest of seas. But it was the Hebron project, whose 65,000-ton topside was the biggest ever moved when it was towed from Korea to Canada, that broke heavy lift records when the whole whopping 750,000-ton megalith was finally maneuvered into position. Oslo, Norway. This is the head office of Kvaerner, famed the world over for its concrete mega-structures. Everything it builds is big. Indeed, it has built not only big oil platforms, but the biggest. Far out in the North Sea are 2 oil and gas fields, the Troll A and the Gullfaks C. Resting above them are 2 of the world's largest structures, respectively the tallest and the heaviest. Off the coast of Newfoundland, 2 other platforms, the massive Hibernia and Hebron, moved into place in spectacular fashion. The Hebron has the biggest topside in the world. When construction on the massive structure was finished in Asia, it was towed in a mega move halfway around the world to be installed onto the platform base in Canada. Kvaerner is specialized in gravity-based supports, massive concrete bases that use gravity to keep an oil platform perfectly in place. Some of these concrete giants float and are held in place by cables, but others simply lie on the sea floor. Not so simply, as we shall see.
Hebron has the heaviest topside ever installed, so it's 65,000 tons weight when it's operating.
Hebron, the last one that was delivered last year, is 133,000 cubic meters of concrete. Troll is 220,000 cubic meters of concrete, and Gullfaks C is 240,000 tons of cubic meter concrete. When it comes to concrete, because concrete is a bulk material, that is always numbered in cubic meters. Not tons when it comes to comparing sizes and so on.
The wild North Sea and northwestern Atlantic Ocean are among the harshest environments in the world. And yet, it is here where some of the most strategic oil and gas fields lie. Icebergs, earthquakes, and winds up to 100 kilometers an hour are just a few of the dangers that await the brave few who venture here. Indeed, the first freak 25-meter wave was recorded in the North Sea on an oil platform. This is the bustling modern city of Oslo, Norway. One of the great centers of the Viking explorers who braved the North Atlantic in open boats to discover the Americas, a historical connection that still ties Canada and Norway. Oslo was also the home to Roald Amundsen, whose ship Maud has recently been saved from the great Canadian North by adventurous salvors. The two countries share a unique understanding of the Arctic North and have learned how to build enormous structures that can survive in the hostile environment. For 3 decades, Norwegian, British, American, and Canadian companies have drilled the seafloor here to extract the black gold. At the heart of the operations was Kvaerner, one of Norway's most experienced oil platform design companies. Kvaerner's story starts in the mountains near Oslo more than 150 years ago, when water mills provided essential energy for manufacturing. With the Industrial Revolution, Kvaerner and their competitor at the time, Aker, began building ships, turbines, stoves, and tools to supply Norway's industrial development. When the North Sea oil fields were discovered at the end of the 1970s, both companies started building oil platforms. They specialized in a type of oil platform called a condi, a concrete platform that sits on the bottom of the sea, using gravity alone to stay upright. In 2002, the two companies merged, and in 2011, Kvaerner was split off as a pure engineering company focused on designing and constructing oil platforms. Here in Fornebu, near Oslo, at the Kvaerner headquarters, Catherine Rusten Haldorsen and Guro Løken work to see that the oil platform projects are not only built safely, but floated to their site of operations successfully.
I'm responsible for marine operation and decommissioning in Kvaerner. So when I joined the company back in 1996, we had just finished towing out the Troll A platform, which is often referred to as the 8 wonders of the world. So I thought that was just amazing for me as a young engineer coming, seeing this operation. And for Troll A, as you might know, it's 472 meters tall. So if you compare that with the Empire State Building, that's huge. The Empire State Building is 442 meters. So for me, Kvaerner was a company that built and installed the most fantastic platforms.
I must say that the worst thing that ever happens is if people get hurt. We want our people to go home safe from work every day.
The engineers and designers at Kvaerner must be confident that no matter how big of a structure they build, they know it will float and survive even the most challenging weather conditions.
The reason why a concrete platform floats is actually that the uplift and the weight is equal, and then we get it to a floating position. You might know about Archimedes' law, and that's the basis for all of this. Basically, when Archimedes put himself into a bathtub, he saw that the displaced water was the same amount of as his weight, basically.
The traditional laws of physics remain the guiding principle, but it is the tried and true engineering experience that assures the platforms are built to last, whether in the ice-clogged North Sea, the northwestern Atlantic, or the placid Adriatic. The North Sea oil fields were first discovered in the 1970s, just as the world was undergoing its first great oil crisis. However, getting to drill there proved a Herculean task. the Norwegians had a solution. The Condeep is an incredibly deep concrete structure that lies on the sea floor and holds the oil that is pumped in massive reservoirs. Catherine Ruston Haldorsen is the head of concrete constructions at Kvaerner and has seen many Condeep sail out of Norway's deep fjords.
Condeep is a concrete deep water structure. And the concrete platform may include oil or gas storage inside, 1 to 4 shafts, mechanical outfitting, and of course drilling equipment. And of course one important feature is it is the foundation for the topside. But I think maybe that in the very early stages, you know, with the extreme water depths, they did not have the technology for anchoring structures to the seabed. Today you see a bit some other solutions than what we had in the early beginning of Condeep platforms.
One of the most challenging oil and gas reservoirs is the Gullfaks field, 175 kilometers northwest of the Norwegian coastal city of Bergen. In the 1970s, 3 Condeeps were built to extract oil, but the last Gullfaks C proved to be a record breaker. The sea floor of the Gullfaks oil field is made of meters and meters of soft clay with the consistency of yogurt. The place was a slope down to the Norwegian trench. Getting at it was incredibly difficult.
Well, of course, if you have a very solid ground, stable ground, you don't necessarily need skirts. But of course, if you have a soft, more yogurt type of soil, you need to ensure that the platform is anchored well into the seabed. And you may use grout and of course air evacuation system to get the trapped air out from the structure.
Protecting the sea from pollution and humans from accidents has become an overall priority for all companies all over the world as oil tankers, wells, and platforms have grown bigger.
It's now clear the explosion that ripped a North Sea platform apart was the world's worst oil field disaster. A task force of naval and civilian ships is still searching 700 square miles of sea around the Piper Alpha platform tonight.
Exxon Valdez, gouged by a reef, more than 8.5 million gallons poured into Prince William Sound, a prime fishing and recreation area.
Frantic efforts underway right now to try to prevent an environmental nightmare along the U.S. Gulf Coast.
Construction techniques in the North Sea and open Atlantic today build on experience from the past to keep workers and the environment safe from such hazards. Platform moves are meticulously planned in simulation centers, for example, and there have been advancements in the core materials such as concrete so it holds up in harsh ocean conditions.
The salt water around the concrete is absolutely no problem. Basically the concrete does not absorb any water. It's very dense and very waterproof.
In order to ensure that the Gullfaks C platform stayed stable and upright, Norwegian contractors' engineers came up with the idea of building concrete skirts that would sink into the clay for 34 meters to provide the horizontal stability and anchoring. They would be sucked into the mud and held in place by concrete grouting that would fill any spaces left for the vacuum to leak. It was an ambitious project and required more steel than it would take to build 15 Eiffel Towers and 200,000 tons of concrete. Construction began in 1986 in a 14-meter deep dry dock. Many months later, the 16 concrete skirts had reached the required height of 34 meters. Then came the construction of the bottom of the oil reservoirs, again, more steel and more concrete. When no more could be done on the land site, and the construction yard was flooded, the base of the Gullfaks C oil platform was floated out into the fjord. The Norwegian fjords offer platform constructors a unique advantage because they are deep. Even deeper than the surrounding mountains are high. The base of the platform was surrounded by barges and boats, and now the upper part of the oil reservoirs could be completed, and then the 4 massive shafts constructed on top of them, slightly leaning inwards to better access the wells and for center of gravity. Now that the construction was complete, the first of the huge lifts that would turn this mass of concrete into a platform could begin. In order to do this, the 330-meter-tall structure had to be towed through the fjords of Norway from Vats to Stord, where the topside was awaiting it.
When we are designing these platforms, of course, you need to make sure that you have something called the center of buoyancy for the platforms, and you have something called the center of gravity for the platforms. So when we are designing platforms, we have to ensure that we have sufficient stability for towing these platforms out. If the stability is not big enough, then you start rolling and you might actually tip over. I mean, basically, when we do tow out of platforms, we have to ensure that we have a positive GM, is what we call it, geometric metrocentric height for the platforms.
This is the most delicate moment of the whole construction of the Gullfaks platform. The concrete towers need to be sunk so that just 7 meters are protruding from the sea surface. This means that the narrower sections of the 4 shafts are under more pressure of water than they were designed for. So, any sign of cracks or leaks would stop the whole operation. It is thoroughly checked as the barges carrying the topside move slowly towards the shafts. The fleet of barges and tugs approaches the concrete structure, and compressed air is pushed into the barges to lift them to the required height. When they are over the structure, they can be reballasted, and slowly the topside sinks onto the towers, the mating complete. Now the whole platform could be raised to its full height out of the water, and pressure on its sides eliminated. A dozen tugs with 160,000 horsepower were needed to move the behemoth, featuring a displacement of 1.5 million tons.
Gullfaks is the heaviest object ever moved. It's 1.5 million tons. So if you have 1.35 million mini beetles, that is what you're actually towing out. And you can imagine doing that with 12 vessels, maneuvering these through the narrow channels is a fantastic sight. You also have to remember that when you have 1.5 million tons moving, it's not that easy to stop it. So that's why we have to do it slow and in a controlled manner.
The Gullfaks C platform was towed slowly through the fjord out to sea by tugs. On the 8th of May, 1989, it arrived on site despite heavy seas. Oil pipes had already been laid to other platforms in the field, so it had to be positioned perfectly. Water was used to ballast the skirts evenly. Slowly, suction devices pushed the skirts more than 20 meters into the clay. Any gaps were filled with concrete to keep the vacuum perfect. But the records set by Gullfaks C platform were to be shattered by a new con-deep built in Norway 10 years later.
A concrete platform that is placed on the seafloor, like Troll and Gullfaks, you can have enormous topsides. So, of course, if you have a floating platform, it's limited how much weight you can have on board. And because if you have a huge, the bigger the topside is, the bigger the hull has to be in order to keep floating, basically, to get enough buoyancy. So often, I mean, when, like in the North Sea, you see that you have around 300-400 meters. We often have condeeps, as we have explained, but when you go 400-500 meters, we end up with the semi-submersible or TLPs, like we have on Hebron, or FPSO, like you see on Varg and other fields.
If Gullfaks was big, then a decade later, the Troll A project was even bigger. At 470 meters tall, it was, at the time, the largest ever energy project supplying Europe with clean natural gas. The Troll gas field is located in the Norwegian Trench, so even deeper than the Gullfaks oil field. The platform that Aker designed and built in its Stavanger plant became the tallest building on the face of the earth. Here too, the platform was designed to be kept in place by concrete skirts that would dig deep into the soft sea floor, sucked in by vacuum. However, although the technique had been tried and tested before, Troll A's height posed some serious problems for designers. The Norwegian fjords, in their stark beauty, are the legendary home of Norway's favorite monster, the troll. The name of the deepest and most dangerous natural gas field, therefore, seemed appropriate, and the monster that Aker, Kvaerner's sister company, built fits the description. It was designed to resist the highest waves, the worst storms, and even earthquakes. The Aker dry dock in Stavanger is the site of construction of the skirts of the Troll A platform. Now came the time for the very first of the towage operations that made the construction of Troll A and its positioning on the sea floor such a spectacular event. The dry dock was flooded and the huge concrete structure began to float. It was towed out to the adjacent fjord to be continued. Out in the fjord, the oil reservoirs were covered with their dome caps and construction began on the shafts. However, once they had reached 60 meters in height, the platform had to be moved again. The fjord here simply was not deep enough.
Basically, part of the concrete platforms is always built in a dry dock. And depending on the total height of the structure, it could be completed in the dry dock, but very often we have done the first part. Then it's being towed out to a deep water site where the remaining structure has been completed. And in some cases, the topside deck is mated in the deep water sites. We try to do as much of construction in the dry dock as possible. Constructing in a deep water site does increase the cost because of all the flotilla, all the barges we need to maintain offices, services and so on in the floating stage.
Construction was fast, as the company employed a new technique known as slip forming, which minimizes the time it takes for concrete to dry, making for a smoother and stronger surface. Once the deeper fjord was reached, The box girders that served to harden the very tall structure were built. These were prefabricated steel structures that were then encased in concrete to stop the four shafts from swaying with the waves. In the meanwhile, workers got on with building the ancillary equipment, the pipes and tubes, electric circuits and gauges.
The majority of the construction method is based on slip-forming technology. It's an hydraulic system that lifts up the forms, and the reinforcement and the concrete is being executed 24 hours a day. So weekends, Christmas, all days. This has many advantages, and that is you reduce the amount of casting joints. So in principle you get a better quality, you get a watertight structure, and of course it's quicker to build. So you save overall construction time for the projects.
Troll A was designed so that the deck was long and narrow, keeping living quarters far from the derrick and working area as an added safety measure. This, in turn, means that the drill shafts are central, while two support shafts are external. As construction continued, the shafts were sunk deeper and deeper to allow better access to the segment under construction. Then came the third great heavy lift operation of the whole project. Time had come for the concrete support to be mated with the deck and all the equipment it carried. The concrete was sunk to within just 6 meters of the top, so subject to far more pressure than it was originally designed for.
For the platform, we have like permanent ballast system in the platform. But in addition, for these temporary phases, we have some temporary ballast pumps so that these operations can go fast enough, because we need to be, normally these operations are weather restricted, so we need to do it within a weather window. So we use ballast pumps, pump in water, pump out water in order to get out of the dock and also in order to mate the topsides on the platform.
Barges carried the long, narrow deck out to the shafts and were pumped with air so that it could be safely fitted over the four shafts. Every connection had to be fit perfectly for the mating operation, which was completed in 30 hours as the barges were emptied of air and the deck lowered. Once the connection had been made, the whole platform could be refloated to its full height. The refloating and towing is usually done when the North Sea weather is at its fairest.
We never know exactly what wind and waves we see, but on board these huge tows, we normally bring a meteorologist with us, and we have weather meetings several times during the day in order to make sure that it's no hurricanes or no unforeseen weather coming up, because then we have to either go into a safe harbor or hold the towing fleet for a while. When we do plan these operations, we do it during summer season in order to make sure that the weather is nice and we have predictable weather. But it's, I mean, what can I say? We need to do detailed engineering, and then we have it under control.
Higher than the Empire State Building, as tall as the Petronas Building in Singapore, the Troll A was the tallest man-made object ever to be moved. On the 10th of May 1995, the tow out to the Troll gas field began.
First of all, you have to maneuver your platform out from the dock where it's constructed. Then you fill water into the dock, and then you have to fill water into the platform so that it doesn't have uncontrolled lift-off. And when you go out of the dock gate, we often have harbor tugs attached to the platform. In addition, we have a towing tug getting us out from the dock gate. And we also hold back with something we called hold back winches. And then we can ensure that we go smoothly out of the dock.
These massive platforms must be towed very slowly out of the dock and maneuvered in a very controlled manner out into the towing channel, never faster than 2 to 3 knots. Today, tests are done at a simulation center, first to make sure that all vessels are towing with the right amount of force to navigate the route successfully. But there must also be a clear chain of command.
So when we have decided what vessels we're going to use for the tow, we invite the captains, and also we always have a tow master. He's kind of the, if you're in the military, you have to have one guy that's in charge of the tow. So he's in charge of the tow and he's giving orders. So what we do is to rehearse the full operations, both the inshore tow and the offshore tow, with all the involved parties, so that we make sure that every small, like you asked, if we're going through a tight corner, we need to make sure that that vessel pulls in the right amount of force.
Tugs began moving the Troll A down the fjord. They had been over the route several times, virtually. The course took the convoy round a very steep bend, but also at some points the clearance between the seafloor and the bottom of the platform was a meter only. An uncharted rock could have stopped the convoy in its tracks and threatened to topple the platform. It took 7 days to go 200 kilometers. The heavy concrete bottom compensated for the tall structure, and when it was over the designated area where gas pipes have been laid, the skirts were slowly deballasted, keeping the whole structure vertical at all times to make sure that when it reached the bottom of the sea, it would sink evenly. In 1996, when it began operating, the platform set the Guinness World Record for the largest offshore gas platform.
Troll was designed for 70 years lifetime, which is extremely long. But of course the design principles and construction methods are similar. But of course continuous improvement and development of both design and method is very important to adapt to new standards and codes today.
A few years later, Aker and Kvaerner merged, and their engineering expertise was recognized the world over. In recent years, Kvaerner has worked on a number of mega projects that have shown that Norwegian know-how in maritime and hydrocarbon affairs is second to none. Kvaerner has built concrete and steel, oil and gas platforms everywhere in the world, but its speciality is concrete. Here on the Adriatic coast lies one of the most recent projects, specially designed to be low on the horizon and invisible from Venice.
One of the benefits with Adriatic LNG is you have established a fake island away from the shoreline, so it basically does not disturb the people and the region there. The terminal itself was built in Algeciras, southern Spain, and towed to Italy. But the two concrete mooring dolphins, which is part of the LNG, was actually built in a ship dock in Venice and then towed out to the platform. The topside was installed in Algeciras in southern Spain and then completed offshore Venice.
The massive terminal is a liquid natural gas regasification plant, one of the largest in Europe, that supplies natural gas delivered by ships to the city of Venice and the industrial port of Mestre. While today's platforms may not break records like the Gullfax or Troll A, they are still marvels of engineering, and there is no shortage of demand for oil and gas extraction platforms across the globe.
During the new concrete platform age since 2003, Kværner has actually delivered 5 new platforms in Spain, Italy, Russia and Canada. And I think that is something that is not necessarily so well known anymore. I mean, we tend to focus a lot on these, previous wonders. But concrete is as applicable today as it was during the Troll and Gullfaks sea age.
One of the newest monster platform designs was actually built on the other side of the world in Canada. The Hebron and Ben Nevis oil field was discovered off the Grand Banks off Newfoundland in 1980, but taken more than 30 years to come online.
The concrete itself, there has been a huge development of concrete the last 20 years. Of course, concrete consists of cement, water, aggregate, sand and coarse. But there is also a lot of admixtures in the concrete. Or a lot is maybe not the right word, but there is admixtures in the concrete that could speeden up the hardening or slow down the hardening. It also makes it more fluid, so you can actually pour heavily reinforced structures. So I would say that with the development that there has been within concrete last 20 years, I see there is hardly any limit on where we can go when it comes to high performance concrete.
Just the base of the Hebron oil platform is 122 meters tall and 130 meters wide at its base. It contains 52 wells and weighs 40,000 tons, made up of 143,000 cubic meters of concrete and 8,000 tons of structural steel and piping.
Hebron, for example, was built to 27 meters in the dry dock before it was towed out to deepwater site. But it depends on how wide the diameter of the platform is, and of course of the water depth in the dry dock. So we need a certain buoyancy to get off the dry dock basement and towed out of the dock.
The enormous base has the dual role of keeping the platform on the ocean floor and at the same time holding up to 1.2 million barrels of oil pumped from below the sea floor. Over the months, the huge structure began to take shape until it was ready to be floated.
Now, I say safety is an extremely important value for us in Kværner, and already in the early design phase, we start planning safe execution, and both for the construction phase, but also for the operational phase. Also, we are extremely proud of having executed Hebron, completed in 2017. We produced more than 23 million man-hours without any lost time incident.
As the huge platform base was floated out to sea for finishing, the second phase of the work could begin, the construction and later transport of the central topside, which included the drilling and utility modules. The dimensions rivaled those of the base, 183 meters long, 75 meters wide, and 113 meters tall, weighing 44,000 metric tons, but with the addition of the accommodation module and derrick, this will rise to 65,000 tons. The tools brought in to do the job were enormous. The des, or derrick, was delivered to the construction site by barge. Getting the derrick off the barge was in itself a delicate operation, as the massive steel building was a high center of gravity. the 3,900-ton drilling support system was delivered to the base. The steel units were delivered by barge and offloaded using SPMTs, or self-propelled modular transports. Transport engineers built 6 towers that were to hold the lifting and skidding system that were key to putting the drilling support system on top of the UPM. 16 strand jacks, each with a capacity of 750 metric tons, were mounted on the 6 lifting towers and attached to 2 35-meter girders on which, in turn, held the 12 skid shoes and 2 kilometers of skid tracks that were key to the movement. The structure was skidded onto the Dutch-owned ship Blue Marlin using 64 1,000-ton skid shoes. These creep along Teflon rails like caterpillars, extending their reach hydraulically and then closing, pulling the load along with it. Now the UPM arrived and had to be offloaded. Here again, skid shoes were the key piece of equipment, and over 2 days the massive steel monster was moved to the shore. It rested on a finger surrounded by sea, allowing barges and tugs to access it with ease, and eventually the whole structure could be lifted onto the massive base, which had been specially designed to withstand the ice and storms of Canada's frigid north.
In Canada, you have challenges with the icebergs. So of course, those platforms are designed for iceberg loads. While other places, you have different kind of ice challenges that you need to design for. Some areas we have earthquake that we need to consider. And of course, the other environmental loads like wind and waves are key factors for designing the structures.
Over 2 days, at a snail's pace, the module moved towards its final resting place. Once it was in place, the lifting towers had to lift the second module, the 3,250-ton derrick or des, into place. The Italian heavy lift company had been engaged also to install the living quarters of the Hebron oil platform. Over the course of the months, the construction of the living quarters was completed in the huge hangar where 2 gantry cranes lifted prefabricated units onto the basic living quarters structure. The living quarter module was 58 meters long and 17 meters wide, no less than 30 meters tall. It was also equipped with a helideck that added instability. Like the DSM, it weighed 4,000 tons. Once again, the lifting towers were called into action and the strand jacks lifted their loads slowly but surely. The living quarter module was hanging from the towers, but needed to be installed at the correct height so that once floating alongside the UPM, it could be easily and swiftly installed. Fagioli built 10 support towers made of tubular steel and installed them on 12 transport beams. These were mounted astride 5 lines of SPMTs, and the whole unit was more than 40 meters high, with a center of gravity 30 meters high, and a tipping angle of just 8 degrees, an extremely unstable building. Now it had to be moved towards the barge that adjusted ballasting as it took on the weight of the living quarters. The living quarters approached the UPM. By the end of 2017, the massive utilities and processing module was ready to be once again skidded onto a massive barge. At the other end of the bay, the rest of the Hebron oil platform had been completed. Once again, the whole gravity-based structure that would one day rest on the ocean floor was sunk beneath the waves.
Well, any project and concept is unique. They are custom made. First of all, they need to adapt to the water depth where they are placed. There is oil and gas storage needs. We have environmental conditions. We have the reservoir. And there may be also linked to other systems or platforms offshore or onshore.
The top side of the Hebron oil platform was floated over it and attached to the protruding central tower. Once again, the whole oil platform was refloated, ready to be towed out.
Every time when I see a group of people put together, doesn't know each other from before, executing projects like this in an excellent manner, that is a big moment, yes. But of course, towing out of structures when you see the work is completed is of course also a good feeling, yes.
Another sunset over the frigid north, where the demand for black gold, the precious natural resources that fuel our everyday life, buried deep beneath the sea, gives impetus to the most massive engineering on Earth.